Your performance on the electrical exam prep indicates a strong foundation in both practical electrical theory and the National Electrical Code, with an overall good grasp of journeyman calculations. Let's break down each module to pinpoint your strengths and areas where focused review could be beneficial. Module 1 covered practical electrical theory. Your average score was 82.5%. This is a solid performance indicating a good understanding of fundamental electrical concepts. Each section within this module scored 80% or higher, demonstrating consistent knowledge across the board. No specific areas for improvement were identified within practical electrical theory. Module 2 focused on the National Electrical Code. Here, your average score was an impressive 95%. This exceptional performance showcases a thorough understanding of the code requirement. With scores consistently at 92% or higher in all sections, your grasp of the National Electrical Code is demonstrably strong. Similar to the previous module, no areas for improvement were specifically identified in the National Electrical Code section. Module 3 tested your journeyman calculation skills. Your average score in this module was 76%. While still a passing grade, it presents an opportunity for improvement compared to your performance in the theory and code modules. A closer look reveals that your performance in sections 51 to 65 was strong at 80%. However, sections 1 to 25 and 26 to 50 scored lower at 76% and 72% respectively. These scores suggest that a targeted review of the calculation concepts covered in these sections could significantly boost your overall performance. In summary, your strengths lie in practical electrical theory and National Electrical Code knowledge. Your calculation skills are generally good, but could benefit from focused practice and review. To further enhance your preparation, consider the following steps. Firstly, dedicate time to reviewing the specific calculation topics covered in sections 1 to 25 and 26 to 50 of Module 3. Pay close attention to areas where you struggled during the practice exam. Secondly, work through additional practice problems related to these topics. This will help solidify your understanding and build confidence in your calculation abilities. Thirdly, consider using various resources, such as textbooks, online tutorials, or practice exams to supplement your review. Fourthly, focus on understanding the underlying principles behind each calculation method rather than simply memorizing formulas. Fifthly, practice applying these calculation methods to real-world scenarios. This will help you develop the problem-solving skills needed to succeed on the actual exam. Sixthly, review the National Electrical Code articles that relate to the calculation problems. This will reinforce your understanding of how the code applies to practical applications. Seventhly, consider the following example of a calculation that might appear in sections 1 to 25, which could involve calculating the voltage drop in a circuit. To calculate voltage drop, you would use the formula voltage drop equals 2 times the resistance of the conductor times the current times the length of the conductor divided by 1000. Knowing how to apply this formula correctly is essential. For example, if you have a 120 volt circuit with a load of 20 amps and you're using number 12 AWG copper wire which has a resistance of approximately 1.588 ohms per 1000 feet and the circuit is 100 feet long, you would calculate the voltage drop as follows. Voltage drop equals 2 times 1.588 ohms times 20 amps times 100 feet divided by 1000, which equals 6.352 volts. This means the voltage at the load will be 120 volts minus 6.352 volts, which equals 113.648 volts. It is important to make sure that the voltage drop is within acceptable limits according to the National Electrical Code. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. Eighthly, another example could include calculating conductor ampacity. To determine the appropriate size conductor for a given load, you need to consider the ampacity of the conductor and any applicable directing factors. For example, if you have a continuous load of 40 amps, you need to size the conductor so that it can carry at least 125% of the continuous load. This means the conductor must be able to carry at least 50 amps. According to NEC Table 310.15b16, a number 6 AWG copper conductor with THHN insulation has an ampacity of 55 amps at 75 degrees Celsius. Therefore, a number 6 AWG copper conductor would be suitable for this application. However, if there are more than 3 current-carrying conductors in a raceway or cable, you need to apply a directing factor to the ampacity of the conductor. For example, if there are 4 to 6 current-carrying conductors, the ampacity must be directed to 80%. In this case, the ampacity of the number 6 AWG copper conductor would be reduced to 44 amps, which is not sufficient for the 50 amps load. Therefore, you would need to use a larger conductor, such as a number 4 AWG copper conductor, which has an ampacity of 70 amps. Ninthly, another example can involve calculating conduit fill. The NEC specifies the maximum percentage of conduit fill allowed for different types of conductors and conduit sizes. The purpose of these requirements is to prevent overheating of the conductors and to ensure that the conductors can be easily pulled into the conduit. To calculate the conduit fill, you need to determine the cross-sectional area of each conductor and the inside area of the conduit. The NEC provides tables that list the cross-sectional area of different types of conductors and the inside area of different sizes of conduit. The percentage of conduit fill is calculated by dividing the sum of the cross-sectional areas of the conductors by the inside area of the conduit and multiplying by 100. For example, if you have 3 number 12 AWG THHN conductors in a 1/2 inch conduit, the cross-sectional area of each conductor is 0.133 square inches, and the inside area of the 1/2 inch conduit is 0.304 square inches. The percentage of conduit fill is calculated as follows: 3 times 0.133 square inches divided by 0.304 square inches times 100, which equals 13.1%. This is well below the maximum allowable conduit fill for 3 or more conductors, which is 40%. Tenthly, let us consider motor calculations. Motor calculations often involve determining the full load current, branch circuit conductor size, and overcurrent protection for motors. These calculations are essential for ensuring the safe and efficient operation of motors. To determine the full load current of a motor, you can use NEC tables 430.247, 430.248, 430.249, and 430.250, which provide the full load currents for different types of motors based on their horsepower and voltage. For example, a 3 horsepower, 230 volts single-phase motor has a full load current of 17 amps according to NEC table 430.248. To determine the minimum size of the branch circuit conductors, you need to multiply the motor's full load current by 125%. This means the conductors must be able to carry at least 21.25 amps. According to NEC table 310.15b16, a number 12 AWG copper conductor with THHN insulation has an ampacity of 30 amps at 75 degrees Celsius, which is sufficient for this application. To determine the maximum size of the overcurrent protection, you can use NEC table 430.52, which provides the maximum allowable overcurrent protection for different types of motors and overcurrent devices. For example, an inverse time circuit breaker can be sized up to 250% of the motor's full load current. In this case, the maximum size of the circuit breaker would be 42.5 amps. However, the next standard size circuit breaker is 45 amps, which can be used in this application. 11thly, let's delve into transformer calculations. Transformer calculations typically involve determining the primary and secondary currents, voltage ratios, and kV ampere ratings of transformers. These calculations are crucial for selecting the appropriate transformer for a specific application and ensuring that the transformer operates within its safe operating limits. To determine the primary and secondary currents of a transformer, you can use the following formulas: primary current equals kV amperes divided by primary voltage, and secondary current equals kV amperes divided by secondary voltage. For example, If you have a 25 kV transformer with a primary voltage of 480 volts and a secondary voltage of 120/240 volts, the primary current would be 52.8 amps, and the secondary current would be either 208.33 amps at 120 volts or 104.17 amps at 240 volts. To determine the appropriate kV-ampere rating of a transformer, you need to consider the total load that the transformer will be supplying. The kV-ampere rating should be at least equal to the total load. It is also important to consider any future load growth when selecting the transformer size. 12thly, grounding and bonding calculations are also very important. Grounding and bonding are essential for protecting people and equipment from electrical shock and fire hazards. Grounding provides a path for fault current to flow back to the source, which causes the overcurrent protection device to trip and to energize the circuit. Bonding ensures that all metal parts of an electrical system are at the same electrical potential, which minimizes the risk of electrical shock. NEC Article 250 provides the requirements for grounding and bonding electrical systems. Grounding electrode conductor size is based on the size of the service entrance conductors. Bonding jumper size is based on the size of the circuit conductors. It is important to follow the NEC requirements carefully to ensure that the electrical system is properly grounded and bonded. By addressing these specific areas and continuing to practice, you will be well equipped to excel on the journeyman electrician exam. Remember to consult the latest edition of the National Electrical Code for the most up-to-date requirements and guidelines.